Alkane nomenclature, an introduction to naming alkanes. Organic molecules come in all shapes and sizes, ranging from very simple alkanes to very complex polymers and natural products. We need a system to name compounds in an organized way. The rules for keeping organic molecule names straight are developed by the International Union of Pure and Applied Chemistry, IUPAC. The system begins with, and then builds from, the simplest organic substances, the alkanes. These molecules contain no functional groups, and their names serve as a platform for more complex compounds later. When drawing alkanes, be aware that the single bonds are always rotating, which leads to an infinite number of shapes for the same molecule. The shapes of these molecules is discussed later in the organic sequence. The first thing to learn are the prefixes for the C1 to C12 alkanes: 1 carbon, methane, 2 carbons, ethane, 3 carbons, propane, etc. Once we get past C4 and butane, the names take on familiar Greek prefixes such as in heptane and octane, and then Latin prefixes in decane and undecane. To check your knowledge, which molecule represents octane? Octane contains 8 carbons, so the fourth option matches. In this question, match the prefixes on the left with the number of carbons they represent on the right. Dodec is 12, oc is 8, non is 9, undec is 11, and eth is 2 carbons. With the prefixes on board, it's time to start naming alkanes. Each of the molecules shown is the same compound, with 12 carbons in a straight chain, which is dodecane. When no substituents or branches are present, the names are simply the appropriate prefix attached to the ending ane to represent an alkane. Here we have dodecane, nonane, and decane. As the molecules get more complicated, the name also gets more complicated. Branched chain alkanes are very common, so we need more rules to help us name compounds convincingly. First off, we must find the longest continuous carbon chain within the molecule. This could be drawn in any direction, so be careful here. Maybe use a highlighter to trace the longest chain. While this molecule has 10 carbons in the longest chain, it is not simply decane as we have not accounted for the branches yet. Secondly, branches follow the same rules as the parent chain but get the ending YL to show that they are attached as substituents. In this case, the branches are methyl and ethyl. Thirdly, we alphabetize the substituents, so ethyl comes before methyl. However, those groups could be in a variety of different places on the chain, so we must go further. We must give the substituent numbers to tell the reader where the groups are located on the parent chain. This could involve numbering from any direction in order to keep the numbers as small as possible. At this point, we have found the longest chain, identified attached substituents, and given the branches logical numbers. Now we have to assemble the complete name. Putting the name together, using the systematic approach of numerical location and names of substituents on the parent chain, gives us 6-ethyl-3-methyldecane for this example. As with much of organic chemistry, the best way to become proficient is to practice examples and then correct any mistakes. What is the longest chain here? In either direction, the longest chain is 11 carbons, so the parent alkane is undecane. In this case, there are 3 of the same substituents attached, methyl. Instead of writing out methyl, 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 we collect these groups together as trimethyl. In terms of substituent locations, we could go from right to left and get 3, 8, and 9, or go from left to right and get the more logical 3, 4, and 9. At this stage, we have the longest chain, undecane, the substituents, trimethyl, and their locations, C3, C4, and C9. Now we have to complete the name. Following the standard format, the numbers go first, followed by substituents, and then the parent alkane. This gives 3, 4, 9, trimethyl undecane. Using the same rules, which name here matches the molecule shown? In any direction, the longest chain is octane. There is 1 ethyl group attached and 4 methyl groups, with their locations being numbered from right to left to keep the numbers as small as possible. This results in 6-ethyl-2,3,4,4-tetramethyl-octane. This example seems more complicated as a branch substituent is present. The longest chain in all directions is nonane. Substituents are then ethyl, methyl, and the branched isopropyl. Keeping the number small gives 3-ethyl-6-isopropyl 5-methyl-nonane. Which one of the 4 possible names matches the structure given? The longest chain is 11 carbons, which matches undecane, so option D is precluded. Substituents on the longest chain are ethyl and 2 methyls, so ethyl dimethyl will be included and alphabetized. Notice that the multiplier here, di, doesn't apply to the alphabetization. The smallest numbers are possible when counting from left to right, so 6-ethyl-3,5-dimethyl-undecane is the answer. When multiple substituents are attached to a cycle, the cycle is usually the parent. Here cyclohexane will be used as the platform, with ethyl, 2-hexyl, and methyl groups as substituents. Notice that the hexyl chain is attached at its second carbon, hence 2-hexyl. The substituents are alphabetized as usual, leading to ethyl, 2-hexyl, and methyl as the order. The branch 2-hexyl is in parentheses to indicate that the number is the point of attachment on that chain. Putting the pieces together, we get 1-ethyl 3,2-hexyl 5-methyl cyclohexane. Notice that the numbers here coincidentally match the alphabetization pattern. This is not always the case in nomenclature. Sometimes it is easier to name cycles as substituents. For example, here, it would be quite complicated to name the rest of the molecule as a substituent on either the cyclopentane or cyclohexane, so they are added as cyclopentyl and cyclohexyl substituents instead. Here you have to match the systematic name with one of 3 possible structures. While each structure contains at least one isobutyl group, only the first and third feature an isopropyl substituent. The third molecule has 2 isobutyl groups, so only the first matches the required substituent and numbering patterns. In this problem, you must match the name to one of 3 quite similar-looking structures. In the first option, the longest chain is only 9 carbons, which does not match the dec-ane parent. The second structure features 2 methyl groups, so dimethyl would be required. This leaves the third molecule, which matches the given name. As nomenclature developed over the years, a series of names used commonly in industry and medicine were adopted for use. The endings match the number of carbons in the group, while the prefix matches the point of attachment or the shape of the substituent. When more complicated substituents are involved, it isn't possible to apply common names. We must therefore name the group systematically, for example here with the 1,3,3-trimethylpentyl substituent. While we could name this molecule several ways, if the cyclohexane is the parent, we must deal with the multi-branched group attached. With the cyclohexane taken care of, everything else in the substituent must be accounted for. With complex branching, it is easier to find the longest chain from the point of attachment to the ring, which in this case is a pentyl group. The substituents within the substituent must then be dealt with. Here there are 3 methyl groups attached, so trimethyl is used. Numbering away from the attachment point, the methyl groups are at C1 and C3. To complete the name, we put the substituent in parentheses to keep it tidy, and then end with the parent cycle. Becoming fluent in alkane nomenclature will set the basis for adding functional groups later. Other useful resources for naming organic compounds may be found in Michigan State's virtual organic textbook, as well as at the IU PAC site.